We present a novel framework for visualizing volume data that allows interactive exploration using proxy images without accessing the original 3D data. There are three types of proxy images: depth, multi-view perspective, and accumulated attenuation. We extend the notion of depth to multiple isosurfaces over volume, which allows us to perform semi-transparent rendering. We can also perform recompositing with different rendering parameters and relighting by approximating normals from depths. We show examples of relighting with specular highlights and proxy-based ambient occlusion. To enable rotation, we extend depth proxy images to multi-view perspective proxy images. We store the degree of distortion and depth for each isosurface. Distortion information, combined with depth, allows us to simulate complex lighting effects, including proxy-based ambient occlusion, for novel views of the object. We now demonstrate examples of rotation and relighting for a synthetic blob dataset. We show relighting with diffuse only, diffuse and specular, and proxy-based ambient occlusion. This image shows multiple composited depth proxy images of a toy car dataset. In the next example, we demonstrate rotation and relighting using both depths and distortion information. This image shows multi-perspective images for 4 isosurfaces of a dataset. We can rotate the car, perform recompositing with different rendering parameters, and apply lighting effects such as proxy-based ambient occlusion to multiple isosurfaces without limiting interaction. We also demonstrate rotation and relighting for a CT head dataset. We do not want to constrain the user, having to use separate images per intensity interval. We present accumulated attenuation proxy images that store accumulated attenuation for a number of intervals in the scalar field domain. Combining depth, multi-view perspective, and accumulated attenuation proxy images together, we can reconstruct a volume-rendered image that can be explored in view and transfer function domain. We can model the final car for each pixel using a combination of linear transformations from the attenuation images using machine learning techniques. When we modify opacity of a feature in the data, we can use the model to quickly and accurately predict the resulting color for a global change in attenuation. We show examples of the synthetic blob, methane pool fire simulation, toy car, and CT head datasets. We can accurately reconstruct the final color even when the transfer function is modified significantly. The next few examples demonstrate depth-aware enhancement using accumulated attenuation for multiple datasets. In our work, attenuation distribution affects color. Since lighting effectively changes color, this relationship does not include lighting computation. We provide a mechanism for highlighting the shape of different intensity intervals. We presented a novel framework for visualizing volume data that allows deferred interactive exploration using proxy images without accessing the original 3D data. Our work is especially useful for preview and exploratory visualization on low-end desktop computers and mobile devices, and for remote and in situ visualization.